On July 21st, 2023, a spacecraft nearly 20 billion kilometers from Earth went silent, not because it broke, because we broke it. A single wrong command sent from a control room at NASA's Jet Propulsion Laboratory tilted Voyager 2's antenna just 2 degrees away from Earth. And in an instant, humanity's most distant working ambassador stopped talking to us entirely. No signal. In. No signal out. A machine older than most of the engineers tracking it, drifting through interstellar space, completely alone, completely deaf to any command we sent. What happened over the next several days became one of the most tense, least publicized rescue operations in the history of deep space exploration. Stay with me, because this actually happened. It's fully documented. And the way NASA got Voyager 2 back is more remarkable than anything a scripted mystery could invent. Let's set the stage properly, because the stakes of that mistake only make sense once you understand exactly where Voyager 2 is and what it took to get there. Launched on August 20th, 1977, 16 days before its twin, Voyager 1, Voyager 2 followed a completely different path through the solar system, one made possible by a rare planetary alignment that happens roughly once every 175 years. That alignment let Voyager 2 use each planet's gravity to slingshot toward the next. And because of it, Voyager 2 remains, to this day, the only spacecraft in human history to have ever visited all 4 of the solar system's giant planets, Jupiter, Saturn, Uranus, and Neptune. It photographed Neptune's Great Dark Spot in 1989, discovered active geysers of nitrogen ice erupting from the surface of Neptune's moon Triton, and gave humanity its only close-up look at Uranus, a planet so strange it rotates almost completely on its side, likely the result of a massive collision billions of years ago. No other mission, before or since, has matched that itinerary. And once Neptune was behind it, Voyager 2 kept going, drifting outward, its instruments still recording long after its planetary tour was officially finished. On November 5th, 2018, Voyager 2 crossed a boundary called the heliopause, the point where the constant outward pressure of our sun's solar wind finally gives way to the thin, cold material drifting between stars. This made it only the second human-made object ever to leave the heliosphere, following Voyager 1's own crossing 6 years earlier, in August 2012. But here's the detail that makes Voyager 2's crossing scientifically priceless in a way its twins wasn't. Voyager 1's plasma science instrument, the specific piece of hardware capable of directly measuring the density and flow of charged particles around the spacecraft, had actually stopped working back in 1980, damaged during its flyby of Saturn. That meant when Voyager 1 crossed into interstellar space in 2012, scientists had to infer what was happening around it indirectly, using other instruments as a workaround. Voyager 2's plasma instrument, by contrast, was still fully functional in 2018, giving researchers their first direct, unambiguous, real-time measurement of what actually happens to charged particles at the exact moment a spacecraft leaves the sun's influence and enters the space between stars. For the first time, humanity had 2 independent data points, gathered from 2 different locations, 6 years and a considerable angular distance apart. That together let scientists begin building an actual 3-dimensional picture of the heliopause, rather than just a single, isolated snapshot. That's the context that makes the events of July 2023 so nerve-wracking to look back on now. Voyager 2 wasn't just an aging relic drifting through the dark for sentiment's sake. It was, and still is, one of exactly 2 active sources of direct, real-time data from interstellar space, a region no other operational spacecraft has ever reached, carrying instruments no other mission currently has the ability to replace. And on that July afternoon in 2023, a single string of commands sent as part of a routine plan sequence accidentally included an instruction that pointed its antenna away from Earth by just 2 degrees, a fraction of a single degree that, across a distance of nearly 20 billion kilometers, was more than enough to break the connection entirely. Here's exactly what NASA did in the days after Voyager 2 went silent and why it worked. Once engineers confirmed the antenna misalignment, they knew a scheduled correction was already built into Voyager 2's onboard programming. A routine reorientation maneuver designed to keep its antenna locked on Earth, set to run automatically on October 15th, 2023. That gave the mission team a fixed date they could count on, nearly 3 months away, but it also meant nearly 3 months of complete silence from a nearly 50-year-old spacecraft drifting through one of the most hostile environments humanity has ever placed a machine into, with no way to check on its condition in the meantime. NASA wasn't willing to simply wait that long. On July 27, 2023, less than a week after the accidental command, engineers at the Deep Space Network's Canberra, Australia facility attempted something the mission team had internally nicknamed an Interstellar Shout. Using the most powerful transmitter in NASA's entire deep space network, part of a 70-meter dish antenna, they sent a command at significantly higher power than any routine instruction ever used with Voyager 2, essentially attempting to shout loudly enough across nearly 20 billion kilometers that the message might still register even with the antenna misaligned, and specifically instructing the spacecraft to reorient itself back toward Earth. Given the distance involved, the round-trip time for that command to reach Voyager 2, and for any response to travel back, was just over 37 hours, meaning the team then had to wait a day and a half, not knowing whether the command had worked, whether it had even been received, or whether Voyager 2 remained functional at all. On August 4th, 2023, NASA got its answer. Voyager 2 began transmitting again, and Mission Control's official update at the time confirmed the spacecraft had resumed sending science and engineering data as though the interruption had never happened. The Interstellar Shout had worked, a genuinely improvised, high-stakes solution that succeeded well ahead of the automatic October. Correction the team had been counting on as its backup plan. It's worth pausing on how remarkable that actually is. This is a machine built with 1970s technology, running a computer with less processing power than a modern digital watch, that momentarily lost all contact with Earth from a distance so vast that light itself takes over 18 hours to make the one-way trip, and engineers still found a way to reach it, verify it was alive, and bring it back online using nothing but a very loud radio signal and careful timing. That near loss in 2023 wasn't an isolated scare either. It sits inside a much longer ongoing story of a spacecraft that has been quietly defying its own expiration date for decades, and the challenges since then have only grown more serious. Like its twin, Voyager 2 runs on a radioisotope thermoelectric generator, a power source fueled by the natural radioactive decay of plutonium-238, and that power output has been fading steadily and predictably since the day it launched, losing a small, fixed amount of usable electricity every single year with no way to replenish it. NASA's engineering team has had to make increasingly difficult decisions as a result, permanently switching off one scientific instrument after another, not because they've broken, but specifically to conserve enough remaining power to keep the spacecraft's heaters and radio transmitter running long enough to keep talking to Earth at all. In September 2024, NASA made the call to permanently turn off Voyager 2's low-energy charged particle instrument, one of the last remaining active science instruments still gathering data from its position in interstellar space, following a similar decision made for Voyager 1's plasma science instrument earlier that same year. These aren't decisions made lightly. Each shutdown is calculated down to the watt, part of a carefully managed power budget. The mission team revisits constantly, trying to squeeze the maximum possible scientific return out of a fixed, shrinking, and completely unreplenishable supply of energy. As of 2026, both Voyager spacecraft are down to just a small handful of functioning instruments each, primarily their magnetometers, still recording the magnetic environment of interstellar space in real time nearly 50 years after launch, using onboard computers that process information at a tiny fraction of the speed of a basic modern calculator. So what has all of this near loss, power rationing, and careful management actually bought us scientifically? This is where the real payoff of Voyager 2's story becomes genuinely fascinating, because the combined data from both spacecraft has done something no single mission ever could. It's given researchers their first real three-dimensional understanding of the boundary separating our solar system from the rest of the galaxy. Before either Voyager crossed the heliopause, scientists worked almost entirely from theoretical models of what that boundary should look like. A thin, relatively uniform shell separating the sun's magnetic influence from the interstellar medium beyond. Voyager 1's crossing, in August 2012, gave researchers their first direct measurement of that transition, but with its plasma. Instrument no longer functional, key pieces of the picture had to be reconstructed indirectly. When Voyager 2 crossed its own section of the heliopause in November 2018 at a different location and angle from its twin, with a fully working plasma instrument still on board, scientists finally had two independent, direct measurements of the same fundamental boundary. Taken years apart from different points in space, what they found surprised them. The heliopause isn't a smooth, uniform bubble at all. It's turbulent, uneven in thickness, and shaped by the sun's roughly 11-year cycle of magnetic activity, in ways researchers hadn't fully anticipated. Voyager 2's data specifically helped confirm that the transition zone at its crossing point was measurably thinner than the one Voyager 1 had passed through 6 years earlier, a real measurable difference that's helped refine models of how our entire solar system pushes back against the interstellar material surrounding it. That's not a minor academic footnote. It fundamentally changed how astrophysicists model the heliosphere, the vast, invisible bubble carved out by our sun's solar wind that shields every planet, moon, and spacecraft within it from the harsher radiation environment of interstellar space. Understanding its actual shape, thickness, and behavior has direct relevance to a wide range of research, from predicting how cosmic radiation levels might change over the coming centuries, to understanding how sun-like stars elsewhere in the galaxy might shape the space around their own planetary systems. And none of that would exist without a genuinely fragile, aging spacecraft continuing to transmit real data from a real, hostile, unexplored environment well past the point anyone in 1977 expected it to still be operating. Which brings us to where things stand right now, heading toward one of the most significant anniversaries in the history of spaceflight. On August 20th, 2027, Voyager 2 will mark 50 full years since its launch, an anniversary its own mission team has openly stated is not guaranteed, but is genuinely within reach if nothing else goes seriously wrong between now and then. Project engineers have been candid in recent public statements that every system aboard both Voyager spacecraft is what's known in the field as single string, meaning there are no backup components left for many of the most critical systems. And a single unexpected failure, whether from a random cosmic ray strike, a degraded solder joint, or simply the accumulated toll of nearly 5 decades in one of the harshest radiation environments in the solar system, could end either mission with very little warning. Current projections from the mission team suggest Voyager 2's radioisotope power source will likely drop below the threshold, needed to keep its instruments and heaters running sometime between 2026 and 2028, a window that's already begun. When that happens, the spacecraft won't be switched off deliberately, and there won't be a dramatic final message. It will simply, gradually, lose the ability to communicate, its last readings drifting into silence as its power finally runs out. Completely, after very possibly outliving every original prediction made about it by more than 4 decades. And that's genuinely worth sitting with for a moment, because there's something remarkable in it that doesn't need a single invented detail to feel profound. A machine built before most of the engineers currently monitoring it were even born, using a computer that processes roughly 81,000 instructions per second, while the phone in your pocket handles tens of billions, has spent nearly 50 years quietly doing exactly what it was asked to do. Going further than any human-made object in history, surviving a communications blackout that could have ended everything, and continuing to send back real, usable, scientifically important data from a region of space no other operational spacecraft has ever reached. So let's bring this story to where it actually stands, honestly, without needing a single invented signal to make the ending land. Because the real ending here, the one actually written into the physics of radioactive decay and orbital mechanics, is quietly one of the most poetic true stories in the entire history of human exploration. When Voyager 2 finally does lose power, whenever that happens between now and the early 2030s, it won't stop moving. It will keep drifting, silently forever, carrying with it the same object that's ridden alongside its twin since 1977, the Golden Record, a 12-inch gold-plated copper disc containing 115 images, natural sounds of Earth like wind, thunder, and animal calls, musical selections spanning cultures across the globe, and greetings recorded in 55 different human languages. It was assembled by a team led by astronomer Carl Sagan, specifically designed to function for at least 1 billion years in the vacuum of space. A genuinely serious engineering requirement, not a sentimental flourish. The idea was never that it would likely be found. The idea was that if it ever was found, whether in 10,000 years or 10 million, it would still play. Voyager 2 isn't heading toward any particular star. Its current trajectory will eventually carry it within roughly 1.7 light years of a star called Ross 248, but not for approximately another 40,000 years, and even that encounter will be a distant pass, not anything resembling an arrival. That timeline is worth actually sitting with because it reframes everything about why this mission matters. Voyager 2 isn't drifting toward an answer. It's drifting as a question, a genuinely open-ended physical 722-kilogram artifact of human civilization, launched during a specific decade, carrying a specific snapshot of who we were and what we sounded like, sent outward with no expectation of reply and no real mechanism for one. That's not a disappointing ending. That's the entire point of the design, and it's exactly why real scientists like Carl Sagan treated the record's contents with the gravity they did, understanding that whatever eventually encounters it, if anything ever does, will be looking at a message with absolutely no chance of a follow-up conversation, no chance to clarify, no chance to add anything more. Meanwhile, back here on Earth, the lessons learned from keeping Voyager 2 alive this long are actively shaping what comes. Next, NASA's interstellar probe concept, currently in early study phases at the Johns Hopkins Applied Physics Laboratory, is being designed specifically as a successor mission, one built from the ground up to survive decades in interstellar space with modern instruments, modern power systems, and a specific goal of reaching much greater distances than either Voyager has managed, potentially launching sometime in the 2030s, if funding and mission planning align. Every hard lesson from Voyager's aging thrusters, its clogged fuel lines, its single-string systems with no backups, its meticulously rationed power budget, is directly informing how that next mission gets designed, making sure whatever comes after Voyager doesn't have to be rescued with a single improvised interstellar shout the way its predecessor was in the summer of 2023. So here's where that leaves us, heading into an anniversary that genuinely might not happen, but genuinely might. Voyager 2 survived a communications blackout that could have ended its mission entirely, using nothing but careful engineering, patient troubleshooting, and a well-timed, unusually powerful radio signal. It handed scientists their first real three-dimensional map of the boundary between our solar system and the rest of the galaxy. And it continues, right now, as you're watching this, to transmit real data from a region of space that remains, to this day, almost entirely unexplored by anything else humanity has ever built. When its power finally runs out, it won't be the end of a mystery. It will be the beginning of a genuinely uninterrupted, silent journey lasting billions of years, carrying a message that was never meant to get a reply, only to be found, someday, by someone, or perhaps by no one at all. So here's what I want to leave you with. Voyager 2 has already outlived its original mission by more than 4 decades, survived a near total loss of contact that could have ended everything in the summer of 2023, and is now closing in on a 50th anniversary its own engineers describe as achievable, but only just. When it finally does go dark, whether that's next year or several years from now, it will keep moving, carrying humanity's message outward forever into a silence with no scheduled return. Do you think we'll ever build anything that matches what these 2 aging machines have accomplished? Or is this simply a record that can't be broken? Tell me what you think in the comments, because Voyager 2 still has real chapters left to write before its power finally runs out, and I'll be here to cover every one of them. Subscribe and turn on notifications, because whatever happens next to this remarkable machine, you'll want to already be here when it does.